Okay. All right. Thank you so much, David, for the kind introduction. And of course, David and I in LSPT, we worked together for many, many years. And in fact, at the University of Cincinnati, we have at Ohio Center for Laser Shock Processing, which was funded by the state of Ohio. And I should put that in the acknowledgement. I somehow forgot, but anyway. And of course, LSPT was very much part of that effort. GE Aviation has also been involved very much in our work and helping us at the center, especially in setting. And the center, apart from laser peening systems, which I will briefly talk about, we also have other surface modification techniques, including shot peening and ultrasonic nanocrystal surface modification, along with a host of other facilities, residual stress characterization, fatigue testing, stress corrosion cracking testing, so on and so forth. Today, what I'm going to talk about is the work of one of my students, Anurag Sharma. This was supported by Airbus. And Domenico is here. He heard him earlier. He's also one of the co-authors and very much involved in this work, which was on aluminum alloy 7075 in the T6 condition. And the materials all came from Airbus. And by the way, it was very nice to hear all the talks so far, even though I'm in my office here at UNT. I just joined here a couple of months ago and I started this new job. So my life has been somewhat crazy, I should say. I kind of miss being just a simple professor going into the lab and doing some experiments with my students. But nevertheless, I should say something a little bit before I get into the depth of my presentation. Really, Anurag's work is the University of North Texas here has a wonderful Department of Material Science and Engineering. There are 19 full-time faculty, very strong in structural metals, in tribology area, also multifunctional materials. We have a wonderful additive manufacturing center for adaptive and agile additive manufacturing, which was set up through $5 million per year funding from the state of Texas. And also there is a materials research facility, and I'm hoping to rebuild or actually at least build some laser peening and surface mechanical surface treatment capabilities here. Right now, everything is still in Cincinnati, and my students are also in Cincinnati. I still have 4 of them close to finishing. Who rely on that center and all the equipment there. So anyway, thank you again, David. I'll need a little more time, so I'm happy that I can get a little more time. All right. So this work, as I mentioned, was supported by Airbus and was Anurag's PhD thesis. And this is only a part of his work that I'm going to present. Ji Song was a research associate with me in Cincinnati, who's now at Virginia Tech. Domenico, as you all well know, is with Airbus in Germany. My colleague Manny, many of you may know, he is a pioneer in laser peening with more than 60 patents on this topic from all the years he spent at GE Aviation developing this technology. And really, GE Aviation, the first laser peening, the B-1 bomber titanium blades, which were laser peen, were all done with the old generation 1 system that was at GE, and then also the systems at LSP Technologies. So anyway, and I would like to acknowledge the support from Airbus as well as the Ohio Center for the Laser Shock Processing. Is really the third frontier project. And the Advanced Materials Characterization Center at UC. Okay, here's just an outline of my talk. I'm going to give you a brief background. Folks have already told you what laser peening is about. I will just point out a couple of things in relation to the technique itself, in terms of some of the mechanisms that are involved and processing parameters. Then I'll present some results on the 7075-T6 alloy condition, both the base material and then what happens after you do these advanced mechanical surface treatments, and then look at the effect of these treatments changes on residual stress changes and on the mechanical properties as well as corrosion and corrosion fatigue, and then conclude my presentation. Okay, so aluminum alloy 7075-T6 is, a well-known high-strength aluminum alloy. They're widely used in the aerospace industry. Here's an example of a Airbus A380 showing various locations.
VJ, if you can hear me, we've lost your voice.
Turn your video off. Not you, no. Tom. Hey, VJ, can you turn your video off? It might be taking more bandwidth.
Gotcha. You haven't sent that thing to Roma yet, have you? That's okay. BJ's, he's in. Hey, BJ, if you can turn off your video and then restart your presentation. We've lost he's actually muted. Can you unmute?
There is.
Yeah, I'm unmuted now.
You're unmuted, yep. So if you can just restart your presentation, I think we're good.
Yeah, I don't know.
And go ahead and turn off your video.
Yeah, I know.
There we go.
I don't know what, why does it say Zoom webinar?
Yeah, that's where you should be.
Can you hear me?
Yeah, we can hear you.
All right. Okay.
But we don't see your presentation. It's disappeared.
Okay. Hang on. There's some issue I'm having here.
Okay.
Hang on. I'll be back on in a second.
Okay.
Okay. What is the problem?
Just gonna mute him because nobody wants to listen to people figure stuff.
Hang on. I don't know what the problem is. Okay, I'm back on. Can you guys hear me?
Yes, we can hear you and we can see your presentation. If you just want to leave it there and walk through it, I think that'll work.
All right. Okay. Thank you. Okay, going back, so 7075 alloy is used in a whole bunch of applications, as you can see. And basically, going into the full screen mode, so it's just taking longer. Okay. Okay, so 7075-T6 is a high-strength aluminum alloy, right? And this is the basic composition of the alloy.
VJ, we're only seeing a sliver of your presentation. I think if you just leave it in your edit mode, present it, that'll work fine for now. Oh, there it is.
Okay. Okay, so basically it's an aluminum zinc magnesium alloy with about 5.5 to 6% zinc, 2% or so magnesium and copper. These are the main strengthening agents or alloying elements. And it achieves its high strength to the T6 treatment, which is a peak-aged condition. So basically the alloy is solution treated, typically around this temperature of 460 to 490, it's quenched and then it's aged at 120 degrees C. So basically this alloy derives its strength through this precipitation. The precipitation proceeds in steps. It involves initially a supersaturated solid solution. You get GP zones, which are almost pure zinc. That's followed by formation of this eta prime, which is a metastable precipitate, and then the equilibrium stable eta phase, right? And the eta prime is the primary strengthening precipitate. However, most aluminum alloys, right, apart from these very fine precipitation that you get, you also have these large intermetallics, typically copper-rich aluminum, copper iron-rich particles. And those are a huge problem in aluminum alloys, not just from the standpoint of limiting fatigue life, but also in terms of the corrosion resistance, because there is like this galvanic coupling, relative to the aluminum matrix. So these tend to be somewhat nobler. So the areas around these precipitates, they typically tend to get attacked. And that's where pitting typically initiates. And then once the pit forms, it's a local area where you have area where fatigue cracks can initiate. So this SEM micrograph here shows, typical microstructure. But as I mentioned, one of the main challenges is that the T6 treatment, although it provides a higher strength because it's peak age condition, it also reduces the corrosion resistance appreciably, right? So compared with many other aluminum alloys. In fact, corrosion and stress corrosion cracking and exfoliation and so on are problems in aluminum alloys. And one of the earliest speakers talked about the marine aluminum alloys, where there again is a similar problem in terms of precipitation of the beta phase along grain boundaries, which then leads to depletion of magnesium around the grain boundaries and gives you localized cracking and then exfoliation where entire grains fall off. So this is a problem, not just in the 7000 series, but in a number of aluminum alloys as well. So these larger intermetallics, typically you'll get pitting to occur around these larger intermetallics, and then before long, cracks start initiating at those locations. So this is one of the problems, but what has been observed is that to some extent, one can control the corrosion and stress corrosion cracking by using the alloy in an overaged condition, as shown here. So the coarsening resistance generally tends to improve with these overaging treatments. However, there is going to be a loss of strength and loss of fatigue strength, as well as normal strengthening is going to be lost because of that. So the question is, if I want to use the alloy in a high strength conditions, then is there a way to simultaneously achieve protection against corrosion and stress corrosion cracking. And so the goal here really is to look at what impact mechanical surface treatments could have on improving the corrosion and stress corrosion cracking resistance of high strength aluminum alloys. So basically, Anurag did this in 2 stages. He first looked into detail at how laser peening and the other technique of ultrasonic nanocrystal surface modification, what kind of microstructural changes they bring about, and in turn, what impact that has on properties and whether one can achieve some kind of a mechanistic understanding of not just the impact of residual stresses or compressive residual stresses, but more importantly, and this is something the earlier speaker alluded to, is that these surface treatments, they are not just about introducing compressive residual stresses, because there are some significant microstructural changes, near surface microstructural changes and gradient microstructures that are produced, which are less understood and which also have a huge impact on the fatigue life. And this is something that, as the previous speaker mentioned, there needs to be a program to really look at how we can take credit for that, especially in life prediction kind of modeling. But anyway, that's another subject altogether. So one is to understand the microstructural changes, and the second is to look at what impact these treatments have on the corrosion behavior and on the mechanical properties. So basically, the materials, as I mentioned, were supplied by Airbus. These were thick plates. And as you know, the properties of these plates can be quite anisotropic. You have an elongated or partially recrystallized kind of grain structure. So it depends very much on whether, the short transverse direction typically is the weakest direction and most prone to fatigue cracking. So we have to take care when you do these sort of treatments and when you do the testing, that you test the material under conditions which are going to be the worst in terms of loading relative to the microstructural features. So 2 techniques. One is laser shock peening without coating. Although Anurag has also looked at the effect of LSP with the ablative tape and then compared it with without coating. And then the UNSM ultrasonic nanocrystal surface modification technique. Characterization of microstructure and residual stress using a host of techniques, typically scanning electron microscopy, energy dispersive spectroscopy, electron backscatter diffraction. And then also to look at the near surface microstructural changes, you use focused ion beam methods to extract tin foils from the near surface regions, and so that we can understand those features, microstructural changes in much more detail. Residual stresses measured by X-ray diffraction, characterizing surface roughness, grain morphology, and then fractography as well. The mechanical property tests, both using hardness, nano indentation tests, principally 3-point bend tests for the mechanical property, as well as the corrosion fatigue test, fatigue as well as corrosion fatigue. And because, when you're dealing with surface treated materials, 3-point bend or 4-point bend tests are generally more suitable because you're able to orient the sample in such a way that you can really test the effect of the mechanical surface treatments. And then corrosion behavior is principally studied using electrochemical impedance spectroscopy, as well as potential dynamic cyclic polarization. Okay, so we have in the Ohio Center for Laser Shock Processing in my former institution, UC, 2 systems. One is a Generation 4 system. These were built by Continuum, and they were kind of custom built patterned along the systems that GE Aviation has in Cincinnati. And in fact, we got a lot of help in building these systems using with a lot of help from GE. So this is a 7-joule system in each leg. It's infrared, and at the frequency of 10 hertz, and the pulse width is around 20 nanoseconds or so. And with a robot system and a cell for the water and, all the safety measures and so on. Besides that, we also had a continuum DLS system, a 3-joule system in the infrared mode, and also the green. So this also had a green laser, so you can actually do some underwater peening. We've done those kinds of studies as well, and actually that has a very remarkable effect, especially when you do the laser peening without using any ablative tape. So this shows a small cell that we had built along with a robot, so you could essentially do peening underwater as well. So we already know how the whole laser peening process works in terms of inducing shock waves into the material and plastic deformation, and which in turn is resisted by the surrounding elastic material, leading to compressive residual stresses. Now, historically, and for many years until now, including now, typically we use an ablative tape, because otherwise the bare metal would be ablated and you get localized surface melting. Associated with that melting and resolidification, you get tensile residual stresses, which typically means not only do you get tensile residual stresses, you can also, the surface roughness considerably changes, you get porosity on the surface, and often you would have to remove that layer of material in order to actually use the part in application. So for the longest time, the tape process was always preferred. But one of the issues, of course, when you use a tape is that ideally you want to produce a patch in which spots are all overlapping, which means that you may require several 4 to 6, sometimes even many more tape exchanges in order to complete the processing. So it really gives you less flexibility in terms of the process itself, and that is what also adds to the cost. All right. Now there are high energy systems, much higher than the 7 joules. In the old days, some of the systems used to be 50 joules, I think. And over a period of time, the laser beam energies have been going down, the spot sizes have been going down, because you could get potentially the same kind of power density at a lower energy and a smaller spot size. But then you have to worry about the shape of the laser beam and this drilling effect that happens when your spot size is extremely small. But increasingly in recent years, many folks have been looking at what if we do not use this ablative tape at all, in which case the bare metal will be ablated. And in a similar way, the plume of plasma that is generated consisting of all these vapor clusters, they could get confined by the water medium and produce similar kinds of effects. So there are some distinct advantages, at least in terms of process flexibility and ability to not use this tape can give you substantial savings in terms of cost. So there are certain, so just comparing the two. So when you do this without a coating, so we've done, Anurag has done this with and without the coating. So if to create a patch like this, you have to use 4 overlap sequences, sometimes many more, depending on the degree of overlap. So each time we've got to change the tape, right? And this is the net effect that you get from laser peening with the tape. When you do this without the coating, on the other hand, so when you use the coating, you don't have any surface melting. It's a purely mechanical effect, and you get fairly high compressive residual stresses. And the degree of surface roughening is also low. But when you do this without a coating, basically no sequencing is required. But in the case of these aluminum alloys, you can see that the surface appearance is completely changed, right? And as I mentioned, you can do this under flowing water or underwater, okay? And when you do this without a tape, you get surface melting and rapid solidification. The surface residual stresses can often be tensile, or slightly compressive, depending on how many, what the pulse density is, how many spots, number of impacts you've put per unit area. But you can see that something has happened to where presumably, you've got some kind of an aluminum oxide layer that has formed. Okay, so what Anurag did, of course, was with regard to these LSPing without the coating, which was coined as SpWC, following the original work of Yuji Sano, who's going to be speaking later, shows the methodology he used for doing this peening without the coating. But prior to selecting what kind of conditions to use for more detailed study, Anurag initially looked at the impact of pulse density, basically changing the degree of overlap and the number of hits per unit area to set up some initial conditions for further study. Okay, so this shows the conditions. Energy is pretty low. The spot sizes are controlled here for these two. So the LSP here is with tape. LSPWC is without the coating, to get approximately the same kind of power density. And these were arrived at based on measurements of the residual stress using X-ray diffraction. So for this, we used the sine squared psi method with a proto-LXRD system, basically using a chromium tube. The diffraction plane is shown here, 311. And to get the residual stresses to the depth, we use electropolishing, remove layers, do the measurement, and then you also account for the stress relaxation and stress gradient due to layer removal that is kind of taken into account in the software itself. So this shows you essentially when you do the laser peening without coating, this is along two directions, the short transverse direction and along the LP direction, two orthogonal directions, the measurement. So you can see that the baseline material is slightly compressive on the surface, but relatively low residual stresses. And one important thing, as I mentioned, is initially Anurag looked at the impact of pulse density. And you see here the surface stress as a function of pulse density is shown. And what he found was that at about 900 pulses per square centimeter, you get some optimal levels of compressive residual stresses in both the directions. So essentially for subsequent studies, chose this 900 pulses. But the important point to realize here is that this shows the residual stress versus depth as a function of distance as well as variations in the pulse density. And you can see that in general, when you do this without a coating, the surface compression actually in some cases can be tensile. You can see here it is tensile in the other direction. But just below the surface, there's a rapid drop, rather a big increase in the compressive residual stress just below the surface. Get away about 10-20 microns below the surface. You have fairly high level of high magnitude of compressive residual stresses to the tune of about -400 in one direction, about -300 in the other direction. And you can see that the depth of compression also goes to about 1 millimeter or so. Now, if you did this with the tape, then the surface compressive stresses would be much higher than the case without, when we don't use a coating. But the magnitude we found was that much lower. So in fact, when you do this without a coating, you can get much higher levels of compression compared with when you use an ablative tape. Based on this study, he chose 900 pulses for processing all the remaining samples. The other technique is basically ultrasonic nanocrystal surface modification. So the difference is that this is really a technique for severe plastic deformation of the surface. It uses a tungsten carbide ball, and you impact the surface at very high frequency on the order of 20,000 to about 40,000 times per second, and which is the tungsten carbide tool is driven ultrasonically. And then basically what happens is you are just like shot peening and even like roller plasticity burnishing, I would say. It's really a variation of that technique. The difference is in low plasticity burnishing, you keep the tool pressed and then you kind of move it along the surface very slowly. Here, you not only have a static force, but you also have a dynamic force whose amplitude can be controlled. So the main variables in this process are the amplitude, that means the depth, the depth to which you hit it, and the feed rate, the rate at which the tool traverses is another variable, and then the static load is another variable. So machine itself is relatively simple. This is the one at UC. It's really, you can even do cylindrical parts, and you place your sample or your coupons out here, and you essentially what you do is you hit it on the surface and you create a patch, and you can vary the speed at which you move the tool, and you can vary the amplitude, as well as you can vary the pitch or the distance between the hits. So you can see that he chose three different conditions here for looking at the effect of UNSM. One is the static load. This is a constant load over and above the dynamic load. The amplitude in terms of how much you're moving the tungsten carbide tool, the feed rate, the rate at which you move the tool, the spacing interval between the hits. And this gives you some idea about how many hits are there per square millimeter. And then the surface stress measurements are shown here. So now one of the things with this technique is that just like in laser peening, wherever you're hitting, you're plastically deforming, the surrounding material wants to constrain that deformation, and you get compressive residual stresses. But the other important thing is, since it's a severe surface plastic deformation technique, you get surface nanocrystallization. Essentially, the grains get broken up into subgrains or crystallites, which high levels of misorientations and very high dislocation density, which also contributes to substantial hardening. So here you can see the difference. Now LSPWC here is compared with UNSM for one of those conditions. And you can see that here is LSP with tape, relatively low at the surface, but the fairly high depth to almost 1 millimeter or so, right? Along the ST orientation and along the orthogonal orientation. The LSPWC, you can see the surface compression because of the melted and recast layer. That surface compression is much lower, but you can get fairly high levels of residual stress just subsurface. The depth of compression is much, much higher. And finally, in the case of the UNSM, you see that the surface stress, the compressive residual stress is very high, much higher, but the depth of compression is much lower, okay? And in fact, one of the things that we have studied, and I wish Anurag had asked him to submit an abstract to this conference, to this workshop, where he has looked at hybrid peening, combining the two processes, and especially for the specific case of both the 7075 aluminum alloy as well as a high entropy alloy. And in fact, you get some very remarkable results when you combine the two techniques, because you can get high compression at the surface like UNSM. If you do LSP first and then followed by UNSM, or do UNSM first followed by LSP, you can get fairly high compressive residual stresses at the surface. But then when you combine the two processes, you can get much deeper. So in fact, one can make this profile look something like this by combining the two processes. But regardless, you can see that UNSM can lead to much higher surface compressive residual stresses, but the depth of compression is somewhat lower than the case of laser peening. The other important quantity is, as I mentioned, the compressive residual stress is just only one part of the problem, right? The other is the change in microstructure and the increase in dislocation density and in the formation of these crystallites, right? Both LSP as well as UNSM, you can regard them as kind of ultra high strain rate deformation, right? It's plastic deformation. So the dislocation density is going to increase. You're going to form subgrains, crystallites, which are highly misoriented. So what that does, the consequence of having crystallites and having high dislocation density is that you get broadening of the diffraction peaks. And the extent of broadening of the diffraction peaks can be used as a measure of the level of plastic strain at the surface, as well as a measure of the crystallite size. So what you notice here is this is the full width half max of the diffraction peak as a function of depth. And what you see here is that in the case of UNSM, when you blow this up, the dislocation density, as I mentioned, with UNSM are much higher than compared with laser shock peening. The crystallite sizes are also much finer. Okay, you can get almost 20, 30, 40 nanometer size crystallites at the surface, and that gives you a much greater extent of broadening compared with the case of LSP. And interestingly, of course, even with LSP without coating, you do have a fair amount of broadening at the surface. At the surface, it's a little lower, but the dislocation density just beneath the surface is actually quite high. Okay, so beyond about 50 microns or so, there's much more plastic strain with LSP compared with UNSM.
Hey, VJ, I'm going to give you, we got a 5 o'clock stop on yours, so I don't know where you are to your presentation. So if you can.
All right, I'll speed it up.
Okay. Yeah, so we've got another talk that's going to start at 5:10. So we need some time to get that set up.
All right, I will go through this very quickly. I'm sorry. I thought I had all day. Anyway, okay, so this is the base microstructure of the aluminum 7075-T6. Basically, you see two kinds of intermetallic particles, bright looking particles here and darker looking particles. The bright looking particles are essentially, you see these are basically magnesium silicon or even can contain higher levels of oxygen. These brighter particles here are aluminum iron copper. And then you also have some brighter particles along subgrain boundaries and along grain boundaries. When you do these EDS maps, you can see that some of these particles are basically magnesium silicides or even magnesium silicate. The other, we fibbed out an area where we could fib out a particle itself. This shows a fib foil. You can see the bright MgZn2 or eta prime precipitates. And this is an area where there's been some depletion. And some of these coarser intermetallics, as I mentioned, are actually aluminum iron silicon compound, which we could show actually has it's a well-known, it's a compound that's well-known. It has a BCC structure with a big lattice parameter. Now, one of the things is that the microstructure of 7075 is fairly complex. As I mentioned, these are STEM EDS maps showing various kinds of precipitates. The fine precipitates are eta prime. Some of these coarser precipitates are eta. Some others are rich in copper and chromium. Some of these coarser precipitates are actually different kinds of compounds, but the fine ones here are MgZn2. Okay. Okay, so when you do this surface laser peening without coating, you get a fairly rough surface, and you can see here that what looks like even some particles and some blowholes and so on. But when you measure the oxygen in some of these porous regions, the oxygen content on the surface is fairly high, on the order of about 65 atomic percent in some cases. So we fibbed out a foil from the near surface region. So this is a lamella cut through the surface. Okay, so what you see here is after laser shock peening without the coating, you have a region where you have the base microstructure, which is shown here, which has the MgZn2 precipitates. But you have a remelted and recast layer, and in this layer you see some very interesting features, right? So you have what look like nanoparticles. These appear relatively dark in this high angle annular dark field image, okay, suggesting that they are actually enriched in oxygen. Okay, so these are oxygen-rich aluminum nanoparticles. Some of them could also be hollow. Okay, so some of them could be just simply voids or bubbles that have kind of clusters which have just collapsed. But what we could show is that these are principally rich in aluminum and oxygen. Okay, so you have a remelted region from the repeated peening. Now, the other important feature that one sees, apart from these recast layer, which is now free of these big precipitates, is there's a very thin layer of aluminum oxide on the surface. Okay, so two important things: clearly distinguishable aluminum oxide layer, which varies in thickness, and you also have these aluminum nanoparticles. And one of the interesting things is that this is now, the previous set of images were done in a scanning electron microscope. Okay, these images here are from a scanning transmission electron microscope at 200,000 volts, much higher resolution. So you notice that features now which are very similar except in much more detail. You have some very ultra fine precipitates and you have these nanoparticles on the surface. And when you do, these could be eta prime or they could be GP zones, which are known to form even at room temperature. You can have an aluminum 7075 alloy sitting at room temperature and you can get precipitation at room temperature. So some of these fine particles could have been produced that way. But the important point here is that the diffraction evidence essentially shows these are micro diffraction patterns taken from individual particles, which show that these are aluminum enriched in oxygen, right? But the interesting thing is there is a one-to-one correspondence of these particles with the surrounding matrix. So even though this plume that has formed and then collapsed, you know, the aluminum particles essentially almost epitaxially solidify with the surrounding matrix, which is very, very interesting. And a little bit of that mismatch is taken up by these misfit dislocations at the surface. Okay, so this is a very, very interesting thing that we have observed, and this work was published in ScriptaMet, and we have submitted another paper to Materialia. So this gives you some idea about how we think this near surface microstructure is forming, but I don't have a whole lot of time.
Yes, we're down to 2 minutes. So Yeah,
Let me
thanks.
just show you some effects on properties. Yeah. So let's go through this. Let me skip this.
VJ, we got 2 minutes left. So if you could summarize quickly, that'd be great.
Yeah, I'm doing that.
Okay.
Sorry about how long it took, but let me show you just some quick results. Some quick results of the corrosion. So let me do. Okay, in terms of the corrosion behavior, we use EIS techniques. And you can see that in the LSP without coating, the polarization resistance is much, much higher, compared with even the UNSM or any of the other cases. So marked improvement in the corrosion resistance. The other important point is that with cyclic polarization tests, again, there's a big increase in the corrosion potential and lowering of the corrosion current. So when you do LSP without a coating, you get big improvement in the corrosion resistance. The other interesting feature is that if you look at tensile properties, these are bend properties, the LSP without coating gives you the highest strength compared with either UNSM or LSP with tape. And lastly, I will show you the results of fatigue. So this shows you what happens in air. So this is baseline material. Both LSPWC and UNSM are comparable in air as far as improvement in the fatigue life and endurance limit is concerned. But when you get to corrosion fatigue, you can see that LSPWC, that is without coating, gives you a huge improvement, much greater improvement in the corrosion resistance. And I believe this is associated with the presence of that thin aluminum oxide on the surface. And we've also done some fractography, which gives you a little bit more insight into.
VJ, I think we're going to stop you here. We hit our 5 o'clock time, and we got to get the other presenter up and running. So thank you very much. We really appreciate what you have here. Realize you've got a lot of great content that I think has good value for the community to understand. So thank you very much, VJ, for your time.
Thank you, and I'm sorry I kind of ran over, but